Hey there, students! Welcome to today's exciting dive into the world of chemistry. Now, imagine this, you're baking a cake and you've got a whole bunch of tiny ingredients. What if I told you that, just like how we use cups or spoons to measure out our ingredients, chemists use something called the mole to measure the amount of substances? It's a little like a chemist's dozen, but this one is far more powerful. The mole is a way of counting particles like atoms and molecules, just as you would count eggs for your cake, but here we are talking 6.023 times 10 raised to the power of 23 of them in just one mole. Yes, that's Avogadro's number. Let's break that down a bit more. One mole of any substance will have exactly 6.023 times 10 raised to the power of 23 particles of that substance. Now, speaking of 6.023 times 10 raised to the power of 23, you might be wondering, what exactly is Avogadro's number? It's a bit like a superpower in the chemistry world. Imagine holding a coin in your hand and then you multiply that coin by billions and billions. That's essentially what Avogadro's number represents. It tells us how many atoms are in exactly 12 grams of carbon-12, the standard for our counting system. This number 6.023 times 10 raised to the power of 23 is so important because it links the microscopic world of atoms and molecules to the macroscopic world we can see. So, when you have 1 mole of something, you can know that it contains 6.023 times 10 raised to the power of 23 particles. Pretty cool, right? Whether you're dealing with atoms like oxygen or molecules like water, this number makes it possible to count them in the lab or even on an industrial scale. Okay, now let's zoom in and talk about a mole of atoms. You see, atoms are incredibly tiny, and so to measure them, we use this concept of the mole. Let's say you have a mole of oxygen atoms. That's 6.023 times 10 raised to the power of 23 oxygen atoms. A huge number, right? But this is the magic of Avogadro's number. It helps us understand just how many particles are involved in chemical reactions. For example, when you're breathing in oxygen, you're inhaling a lot more than just a few oxygen atoms, you're actually taking in trillions of them. 1 mole of oxygen atoms weighs 16 grams, that's the atomic mass of oxygen. Similarly, a mole of calcium atoms with an atomic mass of 40 grams will also contain 6.023 times 10 raised to the power of 23 atoms. So, whether you're dealing with small oxygen atoms or big calcium atoms, the mole helps us measure them. Moving on to molecules. Now, a molecule is like a tiny group of atoms bonded together. So, when we talk about a mole of molecules, we are referring to 6.023 times 10 raised to the power of 23 molecules. Let's take water as an example. 1 mole of water molecules contains 6.023 times 10 raised to the power of 23 molecules of water. The cool thing is, the molar mass of water is 18 grams per mole, meaning 18 grams of water contains 6.023 times 10 raised to the power of 23 water molecules. When you look at a glass of water, you might just see a few milliliters, but inside that glass are trillions of water molecules. Just think about how important this concept is in the lab, where we can easily calculate how much of a substance is involved in a chemical reaction. Moles allow us to scale up the reactions we see in nature into something that we can measure and use. Now, let's see how this all comes into play in chemical reactions. Have you ever wondered how chemists know exactly how much of one substance to mix with another to make a reaction happen? Well, that's where the concept of moles really shines. For example, when hydrogen gas reacts with oxygen gas to form water, the reaction goes like this. Two molecules of hydrogen gas plus one molecule of oxygen gas gives two molecules of water. In chemical formula terms, that's 2H2 gas plus O2 gas gives 2H2O liquid. Now, this means that 2 moles of hydrogen react with 1 mole of oxygen to give 2 moles of water. So, if you have 1 mole of oxygen gas, you'll need 2 moles of hydrogen gas to make the reaction work. This is why knowing the number of moles is essential to make sure we get the right amount of product, and the reaction happens just as expected. This is also how we figure out how much of each reactant we need in the lab. It's all about balancing the moles. Now, you might be wondering, how does this mole concept apply in real life? Well, let's think about the pharmaceutical industry. Chemists use moles to calculate exactly how many molecules of a drug are needed to achieve the right effect in the body. For example, in a painkiller, chemists know exactly how many molecules of the active ingredient need to be present to relieve pain without causing side effects. Moles also help us calculate how much of a reactant we need in industrial processes, like in fertilizer manufacturing or even in the food industry, where moles are used to determine the right quantities of chemicals for flavor and preservatives. The beauty of the mole concept is that it's universal, whether in a chemistry lab, in an industry, or even in a biological system. It's the key to measuring the invisible particles that make everything around us work. So, to sum up, the mole is not just a number, it's a bridge between the atomic world and the world we can see. Whether you're measuring atoms, molecules, or ions, the mole allows us to count vast numbers of particles, making it possible to conduct chemical reactions, produce industrial materials, or even design medicines. Remember, Avogadro's number is 6.023 times 10 raised to the power of 23, and this number is central to understanding how chemical processes happen, from the lab to the real world. The mole concept is essential for everything from simple chemical reactions to complex industrial applications, and that's what makes it so fascinating. Pause, keep this concept in mind, and you'll see chemistry everywhere, in everything from cooking to technology. Thanks for joining me today. I hope this session helped you see how chemistry is more than just equations, it's the invisible force behind the things we see, use, and even taste every day.